yesterday I've had some problems. It was not working properly, so maybe the battery is low. Looks better. Thank you very much.
We want to check your sound.
Test? Of course not. The same problem. After 10 days. So test. Okay. Okay, so good morning everyone. Welcome for day 10, so the last and final day. So I hope you have heard some interesting talks about fundamentals of combustion processes, and we also started to talk about applications. And I will summarize or close today's session with the final presentation about combustion fundamentals of explosion protection. So as an application example, how we can use our knowledge about combustion process to evaluate safety hazards when we use combustibles. So there, one topic of course is the ignition by electrical discharges. Of course we need electrical power everywhere. We need it also in chemical and petrochemical plants. So of course it's of great importance to avoid ignition by electrical discharges. We have several types of protections based on fundamental research, but of course if you would consider details with all the different type of electrical discharges we have, there is some ongoing research here too. So I have presented you already this examination of non-thermal plasmas where we have no breakthrough, where we don't have a spark, but we have heat formation and especially production of radicals due to electron impact reactions. So even though there is no hot plasma here, ignition takes place. Another example is the so-called opening discharge. So for a classical spark, you always need strong voltage. You have to be above the Paschen limit of several hundred volts. But of course, when you have such a closed system which you open, so we have here two electrons in contact. So there is a current flowing through this system, and then we open it. So so you see, when we open it, a spark is formed. So what is happening? The electrodes are in contact, so current is flowing, but then we are opening them, and so we separate them. And in the contact between the two electrons, we reach very high temperatures. So the metal starts to melt, starts to vaporize, and then finally we got a plasma here, consisting also metal atoms and so on. So it's a quite complex configuration. And here we can reach ignition with a voltage around 21 volts. So at very low voltages we also can achieve ignition of combustible air mixtures. So these are totally different ignition processes, but we always talk about ignition by electrical discharges. And today I will focus on the hopefully now well-known minimum ignition energy. So here we talk about normally breakthrough discharges, so very short discharges with respect to time, so 50 to 100 nanoseconds maybe. And the energy is stored in a capacitor, and then for a given spark distance or gap length here, we will see a spark, and the minimum ignition energy finally depends on the shape of these electrodes, of the distance here, and of course of the mixture composition at given pressure and temperature. So for each combustible we know that this has to be adjusted, and the main usage, we have discussed it yesterday already, is to classify combustibles in different explosion groups or gas groups. So here you see it again. So this is a typical discharge, 15 nanoseconds. Within this very short time, the electrical energy is deposited into our hot small plasma volume. So it's a very fast process here. At that time nearly everything can happen, and then we just see some fluctuations here. The electrode distance for the most hydrocarbons and hydrogen are in the range of 0.5 to 1.7 millimeters. So this has several reasons. So the smaller the gap here, the smaller is the breakthrough voltage. And if we look at 1/2 capacitance times U square, of course, the smaller the voltage, the smaller the energy is. So for hydrogen, this can be down to 0.5 millimeter. However, if this is too small, we have, of course, cooling effects here. So there is maybe enough energy, but the flame cannot leave this area because it's cooled from the electrons. So for gases where we need higher energy, we also have to increase the spark gap. So for propane, for example, we need 1.7 millimeters. So there's a rule of thumb. This is in the range of the quenching distance of the combustible we want to examine. So hydrogen has around 0.6 millimeter, so the gap distance here is with 0.5 millimeter in the range of the quenching distance. So in classical setup we can see here, so we have an optical accessible vessel, we have windows here at all sides, and now we want to focus here on 3 representatives for the 3 different gas groups. To C, hydrogen, to B, acetylene, and to A, propane. And you see here 17 microjoule, 82 microjoule, 240 microjoule. These are the respective minimum ignition energy of these combustibles at these specific concentrations. So and when we look into the system here, you see here we have our electrodes. We have now used a top-down configuration. But we can also rotate them by 90 degrees, so this has no influence on the ignition process, or no significant. So we can adjust here these electrodes so that we can optimize the spark gap. We can exchange, of course, the electrodes to test other materials or other shape of the electrodes. And so this is a classical result from literature. So first of all, okay, you have to vary the mixture composition. So you see that at lower, leaner and richer mixtures you need more energy. Near the stoichiometric composition we found somewhere the minimum ignition energy. But as I said to you yesterday, this represents a mixture and an energy where we found in 1 of 100 experiments in ignition. So of course there is a large influence of probability here, and therefore when you compare different literature, you can of course find some deviations here. There is no the absolute minimum energy value. It always of course comes with an error margin, but of course you can see here the main influences, and this we also have discussed already. So the ignition probability, here you have experiments where ignition has occurred. Here we have experiments where no ignition has occurred, so there is an overlap here, and from this we can calculate a probability function which results then in an ignition probability here around 1%, which is corresponding to the experimental MIE value. So so this is what we know. The electrons stored in the capacitance. We have the spark which is forming. So this we have discussed already. The final question is for us always, so what is the real thermal energy? So when we want to compare it with a simple 1D configuration, numerical calculations using simple 1D calculations, normally we neglect all these losses. We just deposit energy to heat up our system. And of course then there is a deviation from the numerical and the experimental results, and this is of course due to the fact that we don't know this precisely, and this we have to examine. So we can use so-called optical emission spectroscopy. So we collect the light from our hot region and use a spectrograph and an image intensifier and a camera to get spectra like these here. And so we vary energy and distance, so we vary energy density here in the experiments and measure then the spectra we see here. So what do we see here? This is the second positive system of nitrogen. So and from the shape of these bands here and the intensity ratio of these different bands here, we can calculate both rotational and vibrational temperatures. So these are not the ambient temperatures we have. The species are just distributed in the energy levels which does not correspond to the ambient temperature. And this is related to the energy we deposit into the system. Of course, after some time, due to collisions, they will fall back to the energy distribution here, and the different levels will fall back to the ambient temperature distribution. But for a short time after excitation, we will see that they are at different energy levels here. And this we can use to analyze the different discharge energies. So here you see in classical view of such a discharge here for hydrogen, so 0.5 millimeter, so maybe 200 micrometer width of this emission we see here. Here we see just the maximum of the intensity, and here we then see the corresponding spectra. And here we have varied the energy. So here we have nearly 4 times, 3.5 times the energy of this experiment. And so from this we can analyze the different lines, bands here to get the corresponding temperatures. So, and we of course have a non-thermal plasma. That means the virtual temperatures of the vibrational and rotational states are not equal to the translational temperatures, that means to the ambient temperatures. And there are often also electron temperatures given in literature, so which may have here then energy levels corresponding to much higher temperatures. So we see here we can vary the distance, we can vary the energy. We see no big influence here. So the rotational temperatures are always around 600, or here 525 degree Kelvin, sorry, and the vibrational temperatures are at much higher levels, so 4000 Kelvin. That means, of course, we have a non-thermal plasma, and this is in agreement with literature. So what is the main influence of this part here? So a lot of energy is deposited here into the vibrationally excited nitrogen, and this is something like an energy storage. So this nitrogen then collides with other molecules, and then the energy is transferred to the other molecules, leading to higher translational velocities, leading to higher temperatures. So we just store the energy here, and finally we need it, of course, for our combustion process. So for Schlieren measurements, so here we have an LED as a light source. We use a pinhole here. We have a lens system here. We have the observation volume here. Then we have a pinhole here, and then here with the camera. That means there are density gradients in the system. The light is deviated in special directions, and this is then deleted by our pinhole. So we see this change of way of light with brighter or darker regions in our GIAN image. So how does it look like? So here we see a temporal series of such of one specific discharge in air. So we have a distance here of 1.7 millimeter and a quite high temperature corresponding to the minimum ignition energy of propane. So here at what is it, 31 nanoseconds after beginning of the discharge, we see here in hot region. So there the energy deposition takes place, and after 150 nanoseconds, so the discharge is now over. Now the electrical energy is deposited into our system. We see here a hot kernel, and this broadens with time, mainly due to heat conduction. And we have to consider here we have heated up very short the system, so from ambient temperature to 3000 Kelvin. So we also have higher pressure here. And so after a given time, so maybe here, so you can see clearly it here, so this pressure expands to the outer atmosphere. So here the pressure then falls back to ambient pressure, and we have a pressure wave which moves with the sound velocity of the cold mixture into the unburned region. And this of course also has a small influence on the temperature field in the surrounding. So and then after 50 milliseconds you see here a deformation of this hot gas kernel. So again, there is no electrical plasma anymore. This is just hot gas we see. And you see here how this is changing. So then we have plasma-induced vortices. So the cold gas mixes with the hot gas. And this of course has also a strong influence on the combustion process. This is something which I will point out later more in detail. So what we can yield from such experiments, so we get the radius of this kernel here as a function of time. So you may see it here. Here there's a small growth, and after this formation of this pressure wave, it's slightly larger. And we can of course examine the propagation of this pressure wave. And so this can be seen here in the experiment. This is the kernel radius, and this is the position of the pressure wave. And what we see clearly here is the higher the initial energy, the larger the kernel is. So the initial volume gets larger when we increase energy. So then here the pressure wave leaves our hot gas system. So we see this enlargement due to this process. Again, here we have high pressure in the volume, which then expands to low pressure. And then here we see more or less a constant radius for up to 10 microseconds. So heat conduction is quite slow, of course. And so we see the same with the pressure wave. So here it leaves the hot region, and then it moves more or less with the sound velocity of the unburned mixture through the system. And again we see an influence of energy here. So the initial radius of course depends on the initial radius here. So the higher the energy, the larger the initial radius for the pressure wave to start. And the interesting thing is, when we assume proper heat losses in the calculations, this will be explained later here. This is just a comparison of numerical calculations. So you see, we see the same effect in the numerical part. The higher the initial energy, the bigger the initial radius of the hot kernel, and the bigger the initial starting radius of the pressure wave. So this initial radius is then an important parameter for the simulation. Again, in the simulation, we deposit energy into a volume. The critical parameter is the energy density. And therefore, of course, the radius is very important here. So the volume is given by the length of the gap and the area of the cylinder, so PR square. This is then, of course, very influential. You see, the higher the energy is, the larger this initial radius is. So we start here around 120 micrometer, go up to 200 micrometers at this low energy. So here we are below 0.5 millijoule. And then when we compare more in detail our experiments with the numerical simulations, so here we have the experiment in black, and these are different numerical calculations where we assumed heat losses. So we just haven't reduced the deposited energy by a factor, assuming heat losses. That means eta equal 1, there are no heat losses, and here we have 80% heat losses. And so you can see here the best comparison for the flame kernel and for the shock wave, pressure wave. We yield with an astonishingly high assumption that 60% of the energy are not stored into the system. So only 40% are used for the ignition process. So, but that's only a small part of the real world. So when we look here into typical ignition events, you see the deposition of the hot energy into the system, and then this flame starts smoothly to have a typical spherical shape. So, of course, at that time the ignition event is no longer of interest. Now the combustion just takes place. But here we can see, hopefully, a little different configuration. You may see that the flame starts earlier on the right side. Again, so you see then an initial vortex formation, and then the ignition starts more on the right side, and then it moves with different velocities on the left and the right side, initial velocities into the system. And so here we have an ignition probability of only 1%, of course. When we use the same energy, we see just nothing. Nothing occurs. So we deposit the energy, and then we have large kernel formation, large vortex formation. So the hot gas and the cold gas are mixing, and finally no ignition is visible. So this we can examine here. Now we have selected images of the video you have seen here. So the three cases. So we have a hot kernel here, So again, 160 microseconds already, so far after the end of the electrical discharge. So here we have a hot kernel which then interacts with the surrounding due to vortices, mixing with the cold atmosphere, and finally in this experiment no ignition occurs. But of course it can happen that there is a clear spherical flame propagation, but also this is visible, that the ignition has taken place here on the right side. So we do not have only to focus on the energy and the volume of the plasma. Here of course we have to consider subsequent fluid interaction of the surrounding with our hot gas kernel. So we can see this even more clearly here with ethylene, so where we have 4 different energies used. So at this low energy, I think so the ignition geht das nicht. So it's difficult here. Okay, what is not visible here, of course, that if we use lower energy, the ignition starts later. So, okay, for the Schlieren evaluation, okay, first we have a background subtraction, so then we get such a clear image, and then we use a specific function to find the edge of these areas, so we get here clear boundaries between burnt and unburnt mixtures. And then in this area here between the red lines, we calculate the distance from the spark, from the initial spark center. So here we get information about left and right radius, and this we can then plot for an examination. So what we see with ethylene, at high energies we can repeat the experiment at different times and we see nearly no difference. So ignition and flame propagation looks more or less identical. If we reduce the energy to 2.9 times the minimum ignition energy, it also looks quite good. But I already had a minimum ignition energy of 2 times the MIE. We can see there's not this classical heating up the initial volume and then subsequent flame propagation. So here with the green results, so we heat up the system and then it takes some time. And then what we see here, it's getting broader, so larger difference. So this has ignited earlier. So how does it work? So in the green case, the upper line, in that experiment it has ignited earlier than in the lower experiment, and this becomes more clearly visible here for this blue part here. So 3 experiments, 2 have ignited quite early, and here in this case it has taken a long time. And what is not shown, of course, are all the experiments where no ignition has taken place. So not only this energy deposition and the volume is of interest. Of course, here we have a long ignition delay time. The mixing with the cold gas in the surrounding is of interest, which then influences, of course, our ignition process. And so this is well known from literature, from colleagues like Derek Bradley. So here in this part, this is dominated by the gas dynamics. So we deposit all the energy in a very small volume, so it expands, the pressure wave leaves the system and so on. And then after a given time, here we have chemistry and diffusion. And of course, this is then the interesting part here, leading to the things we have discussed here. So in hydrogen it looks different. So here we have 4 cases. We can see that it ignites earlier as the flame reaches the outer part later than here. So, but it is not the fact that it had ignited earlier here. It's just that we deposit more energy into the system and the hot kernel is larger. So this can be seen here. So the higher the energy, the larger is this part where the gas dynamics are of importance. And then we have always, with nearly no fluctuations, the flame propagation into the system. And the big difference here is hydrogen Lewis number smaller than 1. For the hydrocarbons we have seen it's larger than 1. That means hydrogen loves this curvature. So this I have explained already in one of the previous lectures. So this is for hydrogen a preferred situation, while propane and ethylene does not prefer the situation, so they have a higher tendency to go out when the curvature is too large. Now here you see it for propane. Again, the high fluctuations. This is due to the fact that these small radiuses of the system, the chemistry is very important, and this is negatively affected by the curvature for propane and ethylene, and positively affected by for hydrogen. So then we can go a little bit more into detail. We have an OH lift setup here, a YAG laser and a dye laser to get a light in the in the range of 283 nanometers to excite OH radicals. We have also a second laser here, which we use to trigger the spark. So why we need to do this? So the experimental setup is just slow, and so we charge our capacitor and then we slowly rise our voltage, and at a specific time we reach the breakthrough voltage and the electrical spark will occur. And due to the fact that this rise in voltage is quite slow, this has nearly no influence on the breakthrough discharge. Nevertheless, when we trigger on this event, we have a problem. This is we have a lot of delay between triggering and firing the laser, getting an image. So we have to trigger on an internal event. And so the breakthrough appears at a given voltage, but it appears due to the fact that we have some startup electron in the system formed by UV radiation from the sun or whatever. And this, of course, is a quite arbitrary process. And with the second laser, we just produce some electrons. That's it. We do not influence the ignition process, but we produce some electrons, and then it starts at the specific time, and we can then trigger the rest of the system and know precisely at which time we have to look. So, and here you see these OH images, again for propane. So here 200 microseconds after the beginning of the discharge, so we only see here hot gas, so there is no discharge anymore. And so we see here at the beginning it starts in the center, so of course there is a temperature distribution here, so near the electrodes it's colder than in the center, and then this enlarges here, and here we also see already some kernels outside the system, but here no ignition takes place. So finally the heating up is again in the center of the system, and for later times we then can see, so now we go, I have explained it different, sorry. So here is the discharge. Here we see, of course, the plasma, and then the temporal evolution goes in this way. So here we have hot gas in the center, and then here we have already the formation of hot pockets outside this this hot kernel. So here the flame starts to propagate into the system. And so here we see it then more in detail. Here no ignition has occurred, so the flame goes out, the initial flame, if there was a flame. And here we see how this flame then finally propagates into the system. And then we can extract these radial profiles at different time steps for different energies, of course. So we see that at a given time, so here we have the hot kernel here with the OH, and then of course the flame propagates to the left and to the right. So this we can then compare with numerical simulations. So of course we have a high fluctuation here in the experiment. So you see here we have 4 different experiments for one energy configuration. So you see a lot of fluctuations here, but in principle we see the same. So the higher the energy, so red to blue to green, the larger the intensity is and the broader the initial volume is. So the energy of course has an influence. And then finally we see that this initial difference is also visible in the difference of the flame positions at a given time. So here this is the spark region, and here we have already the flame region of the system. This we can then to compare use to compare numerical results here with the experimental results. And so we see that this part here is then dominated by the chemistry, so the flame propagation, so the slope of the different curves corresponds quite good. Of course we have some differences here because this is our area of interest here, which we then have to adjust. So come to an end for low energies. We know already a lot. So we know how the energy is coupled into the systems. We know the losses through at the electrodes. So I've shown you an efficiency around 60%. But what we know not yet in detail is the influence of these vortices here we have here. So we have performed only 1D calculations. So you need to perform at least 2D calculations here. So there's still some work in the future. But for low energy discharges, we know the important factors. So energy density, and so on. So this is quite well understood. So OES has shown us no useful trends here concerning the temperature. So at each energy density it looks more or less identical. But Schlieren and OHP-LIV helps us to get more information from the experiments and compare it with numerical results. So with this, normally I would end, but for this lecture I have extended this with maybe 15 more minutes. So as I've said, we now know it for the main combustibles, how this ignition by an electrical discharge takes place and what are the important processes. So for energy from 17 microjoule to 400 microjoule, we think we understand the processes here, what is important. Now, of course, hydrocarbons are no longer of interest. So even though you can see here source of global energy is mainly from hydrocarbons, renewables energy in the whole world have only a small contribution to energy production. We of course have this effect of global warming. So here we see the influence of natural and human factors to the global warming. And I've said in one of the previous lectures, so we have had ice age and hot periods in the Earth before, but this is here the green line. So if we would focus only on the natural factors, we should still have nearly the same temperature like in 1900. So it's man-made what we see here, and this is of course due to the gases with global warming potential like carbon dioxide. So in Germany we are already at 50% where we can use electrical power from renewable energy sources, and for heat, so heat pumps mainly, already 20%, nearly 20% is achieved. And for battery electrical cars, so China is much better here, where they have numbers of 40 to 50%. We have around 7.5% for renewables used in mobility. So this of course is quite a big step away from fossil fuel, but of course there are two big problems: 7 to 100%, 20 to 100%, 50 to 100%, and the sector industry is missing here, so we still need much more energy, which cannot be produced in Germany alone. And the second big problem is, here you see the power production per day over 1 year in 2022. And you see, of course, here we have wind and solar only, large fluctuations. And that's a big problem. There are big differences between peak maximum, peak minimum in a short period. And I was really surprised after kindergarten Another German word is used in English language, that's the so-called Dunkelflaute. Dunkelflaute means we don't have sun and we don't have wind. So somewhere here, for example, you see for a very long period there is no energy production from renewable sources. And so that means we cannot have an energy system based only on renewables. We have to find something to store the energy. So we have seen yesterday this storage with compressed air. That's one possibility, of course. So we can compare here different systems. So I'm surprised that your compressed air system is not here. Maybe you can afterwards explain me where we can find it. But here we have, for example, pump hydro. So there we can store large energy quantities for a quite long time. But also we have very short storage systems, so high power flywheels. So batteries are quite good, but of course the costs are also quite high, so we can use it maybe for smaller quantities of energy, but not for gigawatt. So finally, so I don't know why pump hydro is also in time not higher here, but so chemical storage means we can store large quantities of energy for a very long time. So and this is a typical image we see. Okay, we have our electrical energy from renewable sources. With this we then produce green hydrogen. We can either compress it or liquefy it for transportation with a lot of disadvantages, energy losses and so on. We can transform it to different energy carriers, so carbon capture, Sabatier process, so we can form methanol, formic acid, methane, or use the Fischer-Tropsch process to produce even larger hydrocarbons, synthetic fuels and so on. Also with losses, of course. Then here we have LOHC, so organic hydrogen carriers to transport the hydrogen. We have metal hydrides, we have shortly discussed. This is a possible way. We can use iron, which is not on this list, so we can reduce iron with iron oxide with hydrogen, and then burn this iron in coal power plants to iron oxide, and then again have a circle here reducing, oxidizing this iron. But today I just want to focus on this part here, ammonia. Ammonia, of course, is well known. We can use the Haber-Bosch process. So nitrogen from the air plus hydrogen gives us ammonia. Ammonia can be transported easily. And storage is also no problem for ammonia, even though it's toxic. But then the question is here, the big question mark, age to release. So there's a lot of research necessary. So how to crack ammonia efficiently to get the hydrogen back into the system. And so this we also have already seen. So ammonia itself has a very low burning velocity. So the laminar burning velocity is 6.5 centimeters per second. We need a high ignition energy, and the concept here can be to blend ammonia, for example, with hydrogen. So you see here, when we add hydrogen, we start here at 6.5 centimeters per second and end at 2.3 meters per second. So there's a significantly increase, and we also have a decrease in ignition energy. So what I will show you now in the experiment, there was a question yesterday if you use only mass flow controllers. Here we use a mixing vessel which we evacuate and then fill with air, hydrogen and ammonia using the partial pressure method. And then from this mixing vessel we fill our explosion vessel with the wanted mixture. We have a very small vessel here, just 100 diameter, spherical. So we have a volume only of half a liter, which is normally sufficient for ignition observations, but I of course will show you some limitations later. We can perform pressure measurements, and the ignition source is again a capacitive discharge. And in the previous slides it looks like that we can vary this energy with a large degree of freedom. That's not the fact. So here we have a bank of capacitors which we have to combine to reach specific energy levels. So we cannot yield every energy in the given energy range. We have only selected steps which we can use. So here we see the minimum ignition energy of ammonia for two different distances, 5 millimeter or electrodes, 5 millimeter, distances, 5 millimeter distance and 50 millimeter distance. This is an electron diameter, so larger electrons are here. And here we see the minimum ignition energy at around 21%, so that means an equivalence ratio of 0.9. For hydrogen, this is a little bit broader here. Minimum ignition energy is phi equal 0.7, but it's, as I've said, very broad, so we keep now phi constant for all further experiments, and we add hydrogen from 0 to 20% to the system. So here we have 5 millimeter electrodes and 50 millimeter distance, giving us a minimum ignition energy. For hydrogen we have 2 millimeter electrodes and 0.5 millimeter distance. So of course again big difference. So here we just keep this fixed. So we have 5 millimeter electrodes and 4 millimeter distance. This will give us not the minimum ignition energy for each mixture. Mixture means a specific amount of hydrogen and ammonia, but we want to keep this constant to finally compare also our experimental and numerical results based on one constant factor. So again, this is not the distance leading to the final minimum ignition energy for each combustible mixture here. So how does it look like for the pressure? So again, from 0 to 20% we add hydrogen, and 0 to 20% means of the combustible. So we replace ammonia with hydrogen, and we always have an equivalence ratio of 0.9. So 20% of the combustible is then hydrogen, and here we have then 100% of hydrogen, just for comparison. So you see, for the pure hydrogen event, very fast pressure rise, as we have seen already yesterday, then cooling of the system. So then if we compare this with this pure ammonia plot, so very slow pressure rise, very slow pressure rise. What I have to say here, these T equals 0 corresponds to a given pressure trigger value. Therefore, they are not triggered on the electrode. Otherwise, this blue curve would be somewhere here. So we have here T equals 0 is the time when we reach this specific pressure value. And if we add then hydrogen, you can see how the slope rises, so it's getting faster and faster when we add hydrogen to the system. So this we calculate. First of all, we get higher pressures when we add hydrogen, because the losses at the wall becomes less and less important, and the pressure rises faster, as shown before. When we look now at the ignition energy, so here we have a logarithmic scale. Here we have the experiments where we have seen no ignition in 1 of 10 experiments in black, and in red we have the energy where we have seen ignition in 1 of 10 experiments. So again the problem is we just have here fixed values in our capacitor bank, so there's of course always a step width, so this is not very precise. The error here is quite large. So, but nevertheless you can see when we add hydrogen we will see a decrease of energy necessary for ignition. And here we come to an end. We limit the system to 4 millimeter gap width. And with this there is a minimum breakthrough voltage. And this is here a given energy level. So we cannot increase hydrogen anymore, or we can increase it, but we won't see any influence, because we always would use an energy of this level here. So, and we would always see an ignition. So to continue these experiments we would have to reduce the electrode distance. So then what is the outcome here? So please remember the Schlieren images we have seen at the low energies. I will show this for hydrogen again. So we can see here the energy deposition into the system. We can see the hot kernel. We can see sometimes the plasma discharge. So the deposition time for one image is 33 microseconds. So if we are lucky, the spark is in this time and we can see it, but we cannot always see it. So here we see this bright region here at the beginning, and then already a very large vortex system at these high energies. So 114 millijoule. The old image I've shown, we were around 240 microjoule. So a factor of nearly 1,000 difference. So in this you can see here we have the different amount of hydrogen in the system, and here we have the corresponding minimum energy necessary for ignition. So we start at 0% hydrogen, pure ammonia air mixture. We need 114 millijoule, and we have a very large kernel here. So the plasma of course is quite strong, and here already at 20% of hydrogen we need around 1.1 millijoule, and we nearly can't see the initial hot kernel. And if we would continue this down to pure hydrogen air mixture, we are in the range of 70 microjoule. Of course then it's much smaller again. And then we can see the temporal development. So here in this first image we always see the discharge, and this also is also the reason for this numbers here. We have not t equals 0. Again, we have Schlieren image, so we have a deposition time of 33 microseconds. And the first image is always where we see the first discharge occurring. So it appears maybe at 10 equals 0, but the image started to be taken at 12.9 microseconds for 30 microseconds. So this is the reason for these odd numbers here. And then, okay, we see the formation of the hot kernel after end of the discharge, and you see already this is much bigger than here. And so we increase hydrogen here, and we need to increase energy here. And when we continue then in time, so for these hydrogen dominated mixtures, we can see a nice flame ball with a smooth surface. So ignition has taken place here in the center quite early, and then the flame propagation dominates everything. Here for ammonia, it looks different. So here we have deposited much more energy, so we have a lot of vortices formed due to this plasma interaction. So we have mixing here, strong mixing field, of course, that influence the ignition. But of course we can see it here for the different energies, but again this looks totally different compared to the pure propane or hydrogen results we have seen before. We then again can extract the radius here for further analysis, for example. And here we see the radius as a function of time. So here for pure ammonia we deposit a lot of energy into the system, so the initial radius is quite large. That's again the spark dominated region, and already for 20% of hydrogen this is much smaller. And then after it's given, then we reach the time where the chemistry dominates the system, so we see this flame propagation. And this we get the derivative of this. So we see here a time which is dominated by the spark, and then we get a more or less constant propagation to the outer atmosphere dominated by the flame velocity. This we cannot see for pure ammonia. Our window has only 5 millimeters here in diameter. So already the energy deposition brings us here to the end. But again, for the other gases we can see clearly the difference between spark dominated region and region dominated by the chemistry. So we can compare here these in detail. Also for here given mixture around 10% of hydrogen, when we use different energies, so we see the same effect. The angle, this is again the spark dominated region here, and then we reach the flame dominated region. So for higher energies I've shown you that of course we also have to consider more factors when we want to describe the ignition by an electrical discharge in detail. So we still need of course energy, we need to know the losses, but here you see the strong interaction with the flow field is a very dominant factor, and therefore we can use our simple 1D calculations to get some information here, but finally we have to make the step towards at least 2D or even 3D simulations. So with this I would like to end my today's lecture and my part of this lecture at all. So thank you very much. Thank you. Do you have any questions concerning today's lectures?
Can we say that flame radius is dependent on the minimum ignition energy and the energy deposition rate, irrespective of mixture strength?
It depends. No? So you mean the flame radius depends on ignition energy?
And energy deposition rate.
Yeah, energy deposition rate has less influence, at least for the short times we consider here. And so we have done also some research where we compared 50 nanosecond energy deposition time with 1 millisecond energy deposition time. And there is a specific time where you can see an influence of the deposition rate. But so I think it's somewhere below 1 millisecond it has no influence. How long you deposit the energy, it depends only then on the energy density. But then the flame radius of course depends on the energy you deposit, and of course of the mixture composition. So at the beginning we have the spark dominated region where the energy is the important part, and this also defines the point where we start with the combustion. And then we have the chemistry dominated part, so then we have the subsequent flame propagation.
And in hydrogen and ammonia mixture slide where we have seen 0 to 20% volume percentage of addition of hydrogen, there we had you have said the ignition advance, ignition occurs earlier. So and somewhere we haven't seen the flame kernel when 20% volume of hydrogen is added to that.
Mm-hmm.
So that means what? It's the advance, the ignition is delayed or what?
No, so we see the flame kernel also with 20% of hydrogen.
Yes.
So we see it here. So this is here 20% of hydrogen, the blue line. So here we see the spark dominated region, and here we see then the flame.
Now in that selection image we have seen animation you have just shown us.
The Schlieren image you mean?
Yes.
Yeah. Okay.
9.
You mean this here?
Yes.
So we see clearly here a flame. It's a very smooth, very nice torial flame.
At 2 nanosecond at the beginning.
Here, this you mean?
Yes.
So this is -2 microseconds. Again,
Okay.
we collect here of the gate time is 33 microseconds for one image. So in this 33 microseconds we see this spark here, or this hot region then.
Okay. So that means here the ignition happened earlier.
That's difficult to say. So that's the disadvantage of Schlieren. We cannot separate between hot gas from this plasma and hot gas from combustion processes. We see only hot gas. So we would need eventually here OH live, or maybe better NH2 live if possible, to see clearly where is the flame front. But when you look here, it seems, even though that this case ignited earlier. But again, this is difficult to say. Here we have much more energy deposited, so the gas dynamics from the plasma are dominant here, so it can also have ignited somewhere here, but it's not then the dominating effect for the propagation. So we have no information about ignition delay time. And from the numerical work we have done is, we can say it's difficult to say. There is no clear trend. So you see, we also drastically reduce the energy. The final ignition delay time is, I think, not has not so much big difference between this pure ammonia and this pure hydrogen. Now I have to correct me. So there is a difference, and of course there is a big difference in chemistry. But the question is, when does this start? So if we would compare a pure hydrogen with a pure ammonia flame, hydrogen ignites much earlier. If we have 10% hydrogen and ammonia, this is still igniting like an ammonia flame. So, but maybe here at 20%, the chemistry of hydrogen also becomes dominant. So this we have not examined yet.
Okay, thank you.
Okay, I have a question in continuation to that. So we are mixing ammonia, hydrogen in the pre-mix chamber. Okay, then we are supplying it to the so-called, let us say, a combustor. So does the size and shape of the combustor matters here, or it is the concentration only that matters?
What was the final part? What does matter?
That size, volume or shape of the combustor through where we are doing this combustion.
Yeah, we have optimized this cell. It's a quite small cell with quite small windows to examine the ignition of hydrocarbons and hydrogen, where we need quite low energies and where the combustion is quite fast. So then there is no influence on the walls on the initial process or on the pressure profile. But for slow ammonia, you have seen we reach much lower explosion pressures. So because ammonia ignites in the center, then it goes up, reaches first the top side of the vessel, and then the flame goes down left and right. So here, of course, we have strong losses due to cooling. So this vessel is perfect for examination of ignition of hydrocarbons and hydrogen, where we need low energies, but it already gets some limitations when we look at the ignition process of pure ammonia. So you see here on these initial hot gas kernel formation dominated by the spark already reaches the end of our optical window. So we don't see the subsequent flame propagation. And you are seeing from the pressure profile, then the subsequent flame propagation is also influenced by the small vessel size. For this we have already a bigger vessel, and we want to use it, of course.
Okay. So my next question is a general question. So we know that combustion takes place in the gaseous phase. So is there any, by chance, is it possible it to happen at a solid phase or in the liquid phase?
I think it's coal. Coal is happening in the solid phase. So it depends on the combustible. But there are combustibles where the combustion is also taking place in the solid phase. So for alumina and so on, most of them we have vaporization, and then the combustion takes place in the gas phase. But there is some work with solid, some research work with solid fuel, and there is also work with liquid fuel. But here I'm not the expert.
Yeah, but both of them are first converted to the solid phase. I think the combustible gases, then those gases are in.
You mean to the gas phase?
Yes.
Huh?
Yes.
Yeah, that's for most of the combustible, that's the important step. So if you have a droplet, it has to vaporize. If you have a solid, it has also be transferred to the gas phase, and then combustion takes place in the gas phase. But there are examples. I think it's coal. Coal also burns in the solid phase.
Okay. Okay, my last question is a global question. So from the thermodynamics, we are telling that the temperature of Earth is decreasing, means Earth is cooling. We are saying that Earth is cooling. Earth and the solar planet system is cooling down, and but inside the Earth, temperature is increasing due to global warming something. So how these both are contradicting to each other, and how do you look into that?
How do we hear cooling? Can you please repeat?
Means from the analytics of your geophysicist and other thermodynamicists, that the Earth, the temperature of Earth is being reduced year by year. Means Earth as a planet is cooling as an overall.
So that means we should have an ice age in maybe 10,000 years. Yeah? Yeah, but this can be wrong direction. So you mean that maybe this green curve finally goes down? This is maybe, I think I've read something like this, but I'm not an expert here, of course. But this is natural factors only. The Earth maybe should become cooler. However, we deposit so much carbon dioxide into the atmosphere that this is not the dominant factor at the moment. So in Germany, we can wait until the Gulf Stream would collapse. Then it would become drastically cooler in Germany. So then we would have a new ice age in Germany, but the rest of the Earth has global warming. This can happen. So again, this is maybe the natural trend leading to colder temperatures, but this is not what is dominant here.
Okay, thank you.
Okay, thank you. I have only one question. My question is on fire control and combustion control. So while we are extincting a fire or eliminating a burning or combusting fire, we use different materials, like what we may use water to extinct or chemicals. So my question here is there any chemical reaction between the combustible fuel and the fire extinguisher, or is it by heat transfer the fire is eliminating?
Yeah, okay, so this we haven't discussed in this lecture. So there are fire extinguishers mainly based on brome, fluor, so these halon substances. And they not only cool this, the flame, is halon the correct word? So brome and so on, they catch us some radicals. There are some chemical reactions then leading to the success of these fire extinguishers. So this is of course not only cooling of the system, then water would be sufficient enough, but also some chemical processes. Okay, then let's close this session. Thank you very much.
So we have closed the session.
Mm-hmm.
After, just after 10 minutes break. 10 minutes break. Yes, sir. Make ready.
Okay.
Immediately after 10 minutes we come.
So it was not, I think maybe not only the battery, so you have to hold it clearly there, then it works properly here.
Yes, sir.
When I put it there, it was really difficult.
Connection with this.
So the stage is yours.
caused due to a lot of things in cars. The main reason is the bumps that travel through the wheel, through the tire, to the wheel, through the suspension to the other parts of the vehicle, and this leads to fatigue, and it has a detrimental effect on the life of any automotive plastic, external plastic, and also some important parts like doors. So what we wanted to do is that we wanted to find out the composite properties which we would be using, natural fiber based composites which could reduce vibrations, and then study how feasible those materials are in after utilizing them on the car, and then provide effective comfort to the passengers, because vibration can create certain kind of uncomfortable noise which can lead to bad product reviews and uncomfort. And yeah, we also wanted to make it cost effective. So this is the car door. As you can see, we have divided into several parts like 1, 2, 3, 4, 5, 6, 7, 8. What we have done is that we have just basically made a grid out of it so that we can put our sensors there and just test it and get the value for each data. We did some literature review and we studied how we should approach things, what should be our test setup, what we should be doing, and what are the materials that we can use that has already been tested for noise, vibration, and harshness analysis. So this is what we found. Some people like here used carbon composites which are very expensive. Some use natural rubber which is feasible, but again that's expensive. And synthetic rubbers. Synthetic rubbers are effective, but then producing them and disposing them creates a lot of pollution. So that's the reason why we are looking for a natural fiber based alternative. So this is our test setup. So as you can see, we have a rigid frame. On the rigid frame we have just used the bungee cords to arrest our door horizontally. What we are trying to do is that we are trying to create a free condition. Free condition in the sense, let's say that this is a mass and there is no force acting on it. This is W, it's natural weight, and what we are trying to do is negate the weight and make it a free condition so that no force is acting on it. That's how we will be able to find its natural frequency. So the natural frequency is the frequency at which the amplitude of the vibration, the displacement, is at its maximum. Now there is not one single natural frequency for every single point in this area. There are different modal points. So we are trying to find a modal point on this that will help us get the overall idea of the entire door. I'll go back to different slide. Yeah, here as you can see. So what I'm trying to say is that this point will have a different natural frequency. This point will have a different natural frequency. This point will have a different natural frequency. So we want to see which is a common natural frequency so that we can say that yes, this is the natural frequency of the entire door. We are trying to find a common natural frequency. So this is we used Brule and Kager FFT analyzer DAQ system. We used Brule and Kager accelerometer. We put it on each and every single point number 1, point number 2, point number 3, and so on. And then we use the impact hammer to take the reading 3 times and take the average, and that's how we get the entire reading. This is the experimental test setup. As you can see, we have put our sensor there, and what we do, we just take the hammer and hit it. So the accelerometer sends the vibration data to the DAQ analyzer, FFT analyzer, and then it sends it to the laptop, processing laptop, where we can see the data on this software. This is called RT Photon Pro. So this is how it analyzes. So I'll just give you a very short brief about what it does. That is the actually first input that we get. That is how the displacement is over time and acceleration is over time. And this is for the impact hammer, how hard we have hit. This tells us the force and how it's over time it decreases. And this is coherence. Coherence basically tells us how accurate our reading is on each particular natural frequency. So here we can see it's somewhere around 1. So it compares reading number 1 to reading number 2, coherence. So the closer it is to 1, the better it is. So the minimum bar we have set for each reading is 0.8, because below that then the accuracy is very questionable. And this is the main output that we get, which is of our interest, where we study what is the damping ratio there. So vibrations cannot be eliminated, because wherever there is mass, there is stiffness, there is going to be vibration. What we can do best is just increase the damping. When we increase the damping, the displacement reduces, the intensity of the vibration decreases. So that's why we try to increase the damping. So what this software does is, this software uses 3 dB method or half energy method to calculate damping. So as you can see here, this one red line, this indicates its natural frequency, and these 2 points are 3 dB. So this is 3 dB less and this is 3 dB less. So it gives us two other frequencies, F1 and F2, and it just uses for Q is equals to F0 by F2 minus F1. That's how it gives us Q, and using certain formula we get the damping percentage. So after going through the literature, we decided that these 3 materials are the most feasible ones that we can easily purchase in India. So we bought these and made composite materials out of these. Jute, pure cotton and hemp, these all are roughly 100% pure. Cotton is 100% pure, but jute and hemp, they use certain kind of linen to make it feasible to make it a fabric. And here we tested, this is the reading, this is the same reading we saw in this slide. This slide. So this is the same reading, and we see that for point number 3, this is the natural frequency, somewhere around 70, and we tested it, we got the reading, and we got a coherence of 0.9. So we were sure that this is the first resonant frequency or the first modal frequency. And then we collected data for every single point, and we saw what is happening, and then we saw this is the first common big peak where most of the points are responding to. So we went more into details and saw what's going on here. We then find out that there is a low damping area and there is high damping area, and then that's how we segregated both of them. So these are the points which showed low damping percentage for about 3%, 2%, and that was their average damping percentage. This is the damping ratio, we have just told it in terms of percentage. And then as you see 2, 3, 4, 5, 8, 9, and that's how we mark this area. So this is the area where there is low damping. Other than that, every single area has sufficient enough damping. So to increase the damping of those of the structure, we made composites from cotton fiber, hemp fiber and jute fiber, and we applied it behind the door, and then tested on the low damping area again to see what impact it has or how much the damping has improved. So we tested for 1 mm, 2 mm, 3 mm respectively for each of the materials, and this is baseline, like without any material. The average low damping area was 3.34, and after improvement we got somewhere around 5.2, 4.69 and 4.79 after testing. So we improved somewhere around 30%. We got 30% improvement from before. This image will help us understand better for every single point what's happening. So this is for hemp, cotton and jute. When we apply 1 mm and 2 mm, we don't see a significant difference, but as soon as we apply 3 mm, which is the thickness of the sheet
और एक पानी बोतल रख लो. Trivedi, mechanical engineering. He is having a company as a project director. Inside the campus, 600 companies, technology innovation hub. He is handling various projects from the ministry. The project
But you're also a professor, full
Yeah.
professor, yeah. Okay.
He has a lot of integration during the last 2 years. And he gave the financial support to this company.
During our workshop 2 years ago, yeah.
Because I was looking how to handle that
Mm.
So that point of time it was he has been helpful to us. Any kind of new initiatives that we can go forward, like startup companies,
Mm.
Please. Which one? Control and then
Seems to be a bit closing procedure.
yeah.
So how you find the students?
Was good. Was good. Mostly we have only experts.
सर्टिफिकेट दे देंगे ना. डब तुम्ही याते येते याते सर्टिफिकेट दे दियो. चेयर पर निकाल.
So तुम्ही তাৰ পৰা ফটো লৈ
hello, hello.
বুজি পাইছে দুজন মানে কি বেলেঞ্চ নাই বুলি
Start. So very good afternoon to all of you. So we are now in the last stage of this course, GIAN course, that is combustion theory and applications. So in this valedictory sections, we have with us Professor S.K. Dwivedi. He is in the Department of Mechanical Engineering. He is also heading a company. I don't know many of you know or not, but there is a company, Section 8 company in this campus, and he is a project director of that company, and he is handling lot of projects, sponsored projects, startups, and many other activities. During his speech, he will address all the activities that is going on, and some of you also may be expert gives maybe avail those facilities and apply them in your day-to-day activity. And also we all know that the foreign expert of this course, Professor Markus, is also here. So I request both of them, please come to the dais. Being the course coordinator of this GIAN course, it is my responsibility to summarize the activities that we have done in last 10 days. So mostly the course was designed on the topic combustion theory and applications, which is the day-to-day life we are experiencing the combustion in variety forum. At the same time, we also the combustion is also a very is valuable technology for in the transport sector and space sector and cooking applications. So its application is in the area of variety of areas, starting from the common man to moving to space. So all these things we try to cover the mainly theory and some of the phenomena, because we have been emphasizing that combustion system involves the fuel air mixture, which is initially has their own identity, and after it forms the products, they don't have any identity when they are mixed. So that way it is very challenging that all the events or combustion phenomena occurs in the nanoseconds to up to millisecond. So in the short duration phenomena, modeling the chemical species is quite difficult task, and in fact there is no standard theory available to us. So in these aspects
Professor Markus has elaborated the various activities, various modeling, softwares, chemical kinetics aspects, everything he has told us, so that you can take it as our future requirement in the form of research and in research and other studies. So this is briefly about this course, and apart from that, we also emphasize the new technology of the combustions. Normally we call them green combustion, and those green combustion involves the combustions through bio route. So we have biofuel study, we have to minimize the fossil fuel consumptions, we have reference to dual fuel combustion modes, and also most importantly new generations we are going for hydrogen combustions. So route of getting hydrogen combustions from either methane or ammonia, these are the quite challenging task. And in this aspect also Professor Markus has elaborated the new technology of the combustions. Now coming back to this is the overall course summary, and this course was designed for audience like mechanical streams, aerospace streams. We have also energy engineering, all the streams were there. And although we get lot of registration, I mean expression of interest, but finally total registration comes out to be 26, and it was operated in hybrid mode. 10 were in online and 16 of them were offline. Now coming back to the different other activities, that the type of audience are mainly students from BTech level, MTech level, then PhDs, postdocs, all of them are here. So through this activity or interactions, there are many takeaways from them that they can explore their higher study. Maybe I believe that Professor Markus will definitely help you down the line. You have anyway we have contact with him in various forums, fellowships programs. You can take the advantage. That is one way. Second is we also have Professor Markus. He also visited NIT Meghalaya and met director of NIT Meghalaya in last week. There are some plans that they are making collaboration with PTV team Germany, and in the next week. So that is the another activity or requirement of this GIAN course as a whole. So let us thank him that he has kindly consented to Professor Mahanta, and maybe next week who is the director of NIT Meghalaya, and they are visiting to get some MOE or some collaboration mode to get signed, or it is starting the initiatives. Apart from that, he has also interacted faculty members, head School of Energy Science and Engineering yesterday, and also the team from Energy Science also will meet soon, maybe after some time. So that way collaboration is also with School of Energy Science and Engineering of IIT Guwahati. Again we have Dr. Nelson Muthu, he is from IIT Palakkad. Please come, and he with my invitation he joined here. Probably some possible collaboration with IIT Palakkad can happen. Additionally, we have also faculties from KIT Bhubaneswar, Anil and Dr. Anil and Santosh, Dr. Santosh. They are also initiated some collaborative discussions maybe in the down the line, and that is in the pipeline, that is going to happen soon. So apart from that, I am anyway there, and I hope, I believe that he will definitely help at in the down the line for all the requirement that we need in the course of time. So my special thanks to him, and he has kindly agreed to come from all the way from Germany to here, and this 2 weeks course, I think it's very difficult to stay here for a foreign expert for a longer durations, and he has kindly agreed for this. So my sincere thank from my bottom of heart to Professor Markus. And again for Professor Dwivedi, he has also helped the main initiation of this GIAN course program, because 2 years back the team from PTB visited to this campus, and they were in a positions to industry academia meet on deployment of hydrogen energy concept in the framework means new carrier, hydrogen as a new energy carrier, and how it can be implemented those technology globally as well as in particular India and Northeast regions. So during that point of time, we received financial support to organize that event through TIH Section 8 company, and Professor S.K. Dwivedi was the project director, and he has given financial support to hold that event, and the course modeling starts from that day. So when I put a request to Professor Markus, the course initiation started from that day, and which we are going to conclude today. So this is what the background of this course. Of course, many things are in not my hand. It was approved maybe 6 months back, this course. So that is the 2 years back when this event started, and this is the final things. And it is, I'm not going to stop here. Probably the network connectivity among our students in future directions will also give a larger domain. So that is the hope that we are expecting down the line. So as far as this is a most academic part, and the non-academic part, I think it is mostly for maybe for foreign experts, whether they like our Indian culture, whether they like our food, because 10 days is a long durations to manage Indian food, because over the year it's only Indian food he is taking. So that food in taking the guest house, it is taking in the street food in our fancy bazaar. So that way he enjoys the food, and in Indian viewpoint our course is not complete if the food is not good. So that way he gave a green signal that at least he served well. Again, this is all about, I need to talk about brief concept about this course overview. So the plan of activity is that after this, now our next activity, our Professor Markus will give his speech, and then Professor Dwivedi, he will also give his valedictory speech, and towards the end we are going to distribute the certificates. So now I request Professor Markus to give his feedback, honest feedback to us, and if there are any shortfalls, maybe future courses we can implement them. So now I request Professor Markus to kindly address.
So, dear colleagues, dear students, I of course can clearly point out that I have enjoyed the Indian food, and I have really enjoyed the quiet and nice atmosphere here at IIT Guwahati, which is a special place, I think, especially for science. So we have had 2 weeks of combustions here and applications. So lectures given by me and by Professor Sahoo about this topic. I hope you have not suffered too much during the first week when we have focused more on theory. And I hope you have enjoyed the second week when we have talked about applications. And there's one important point. So everyone is talking about replacement of fossil fuels today, so get rid of classical combustion engines and so on. But also in the future we need engineers who are able to deal with the problem of combustion processes. So even though we may have to consider new energy carriers like ammonia and so on, there always will be a combustion process. An application, for specific application, for airplanes, for heavy duty transport, for ships. A lot of application we still need combustion, maybe with other energy carriers, but still we need combustion. So I hope you have enjoyed it, and I hope I have strengthened your confidence here as mechanical engineers mainly to continue studying on this topic. So GIAN means Global Initiative of Academic Networks. And I hope, at least for me, it was a great start, continuation of this networking between PTB and IIT Guwahati. So I have enjoyed your talks and discussing with you about your research topics. And I have enjoyed the visit of NIT Meghalaya. It was very impressive to go there, and hope to visit the new campus soon. Also, of course, I hope to come back again. So this should be the start of our network. So I would like to come to an end. I have to thank you all for participation here. And of course, I have to thank Professor Sahoo for all the organization. Of course, I have to thank the Indian government for supporting this trip, but the most of the work was done from you. So it's not such an easy application. So I'm really happy that I've had the chance to be here, and I hope I can come back again. Thank you.
Thank you, Professor Markus, and it's definite that the network will keep on happening and it will move on. So before I invite Professor Dwivedi, I also request the participants to just share feedback. Please come and share your feedback. You can start from here. Mebratu. Each one of you should come and speak about this course, few words. Or anyone, whoever wants to come first, please come.
Good afternoon, all. I am Dr. Santosh Kumar Hutta. I am from KIT Bhubaneswar. I was a student here during my master's and PhD. I joined KIT in 2019, and then from there I am continuing. So I would thanks Professor Sahoo and Professor Markus and the CET IIT Guwahati for the painstaking effort for arranging this event, and it was a great learning experience where Professor Sahoo and Markus take us through the combustion chemistry basics and revise the combustion theories. Then again they took us through the advanced applications like laser diagnosis and the combustion, how to protect if there are some kind of mishappenings when there are combustion. So with along with that, I'll be definitely going to, since my research area was on combustion, I'm going to definitely work further in this area. And I would again like to request Professor Markus for the discussions what we had earlier during the start of this course for the collaborations. Thank you.
Good afternoon, everyone. So, myself, Dr. Anil Kumar Raut. So, I was also a student here and doing PhD under Professor Sahoo sir. And so, honorable dignitaries on the dais and all the participants and sir. So, it was really cold outside, but it was really hot inside. So, started with spark and then continued till combustion and then ended with blast. And ultimately, how to control this blast and how to control the spark and how to control the combustion processes with the applications. That was one part. And another part was how to utilize all these combustion processes in your day-to-day life, starting from your burning your food from the stomach till burning the fuel in the rockets. So till going towards the mining area where the protection is required, and we have discussed everything with Professor Markus and Professor Sahoo sir. So telling frankly, this was my third interaction with Professor Markus, because when he was here for this hydrogen conference, we had one meeting, and in 22 July, I had a visit to his lab. So I had I got a little very small chance to interact with him, because I was not affiliated directly to his lab. So when I heard that he was coming here, so my first decision was to join with him and talk with him for the future collaborations that I just initiated there. So thank you, sir. So we will just go on continuing the proposal what we have just initiated and what was with our previous plan. So hope we will be in touch throughout the year. Okay, thank you. Thank you for all your things.
Anyone wants to give feedback?
Yeah, good afternoon to everyone. So myself, Dr. Kiran Kumar. So 2 weeks back only, I reported here as a postdoc fellow here under Professor Sahoo sir. So first of all, I would like to congratulate the entire organizing committee, for successfully conducted this workshop on combustion theory and applications. So, so regarding this combustion, so during my PhD work, I worked on metal films porous media, that heat transfer enhancement. So during that time, so I was worked mainly on porous media, that is especially like metal films. So now it is a combustion process, how this and its applications. So when I came to this lectures after this course, so how to relate my work with respect to this combustion process, how we can introduce this metal foam for a combustion process, how it will be better. So as sir has suggested, like a frame arrestor, so how we can use this wire meshes, so that I will work on, sir. So in future I may require your help and guidance, so hopefully I will get it. So yes, of course in this course it has covered some fundamentals, strong fundamentals, as well as some applications like diffusion, flames, and pilot evaporations and all those things. So it was a great learning experience for me, sir. So in future also, if it is possible, some hands-on sessions like computational tools, like if it is possible, like you have mentioned Cantera. So if it is possible, it will be a great opportunity for us to learn and contribute to the society. So overall, it's a great experience for us. So thank you, Nanda.
Good afternoon to all of you and the esteemed members present here. So first of all, I would like to thanks Professor Markus sir and the initiation taken by Professor Sahoo sir to organize this event. And I would like to tell that the things that has been covered here, the basic applications and the combustion theory that has been discussed here is great. And apart from the fundamentals that I have learned, the applications of the combustions that has been discussed by Professor Markus sir, it was a great experience for me to get the idea that was going on regarding this field. And the great thing which I experience is how Professor Markus sir interact with us, and especially the doubts has been taken in a great way. The each doubts which has been covered by him to especially the students that have asking to him regarding the work, because it is not affiliated to direct our work, but since the small doubts which have been cleared by Markus by taking time, so that the things which fascinated me. And also I like to thanks again the CT and also the professor to continuing all these things, and in future maybe if such session could be organized, then it will be grateful for us student community, sir. Thank you so much, sir.
Good evening, everyone. Good evening, sir. I would like to thank you for all the effort you have taken of making the PPTs, of going through them, revising them, and teaching them to us very clearly. I was clueless to the idea of the measurement techniques used, LIF and PIV. I was literally clueless, but I learned about them, and that's how it began for me. And then I also kept on learning about combustion and everything. So it was an eye-opener for me, and I think it has made me motivated to pursue research in this area. It has opened a new door for me entirely. So I would also consider this as one of the PhD areas that I would like to pursue. So I would like to thank you, sir. Thank you so much for giving me this big insight. Thank you for interacting with us, and I would also like to thank all the participants here for making their PPTs and giving a brief introduction to their projects and explaining them very well. Thank you so much, everyone. Thank you, Dr. Sahoo. Thank you, sir.
Anyone? Okay, good evening, everyone. I would like to thank all of you here. Besides that, I would like to thank the organizing committee. When I came to the course, as you know that I came across so many courses during my BTech, MTech, as well as PhD course, but I did not come across with full combustion theory and application. In between, we may take as a chapter in some course, we may take combustion as a chapter, but in course level, I'm happy to have this one, and I hope it will give a good it will build a good profile for me as a course. I'm happy to have this one. Thank you.
Any feedback from CET staff side? One or two, just for, because you people have helped us to organize this event successfully, and I was very fascinated the kind of facility what we have live streaming kind of recording. It's a full recording. It was highly appreciated. And if you are free to give any feedback for us. Okay. Okay. Now I request Professor Dwivedi to share his views, and he has listened to all of us. Now he will conclude with what is his final remarks about the where we stand in this course. Thank you.
Okay. So let me first congratulate Professor Sahoo and Professor Markus successfully completing this GIAN course. I hope all of you have enjoyed this course, and most probably it will be converted to a MOOCs course after few days. And I have seen that there are 18 lectures and 10 tutorial classes also in this. So I hope you have enjoyed all the lectures and the tutorial class, hands-on practice session. And this is a very good course that regarding combustion. So as some of you are told that it starts with your biological systems also, they have taught the biological system along with finally to the space structure also they have covered. So lot of things they have covered in this course, and I hope you have enjoyed and you will take it forward, and you will apply those things in your colleges. Some of your faculty members are also here, so you can float some of the topics as the BTP topics or your MTP topic, and some of you have already expressed your desire to continue as your PhD topic and postdoctoral topics also. So I hope you will continue with the things what you have learned from here. And in addition to that, I request some of you, if you have come forward and develop some sensors, particularly Professor Sahoo has already developed some temperature sensor for transient analysis. Similarly, if you can develop some of the sensors, then TIH also will be happy. TIH Technology Innovation Hub here will happy to sponsor you for developing those sensors. So let me tell briefly regarding this TIH. What is TIH? So there are 23 Technology Innovation Hub in our country. So previously there were 25, now 2 has been reduced. So there are 23 TIH, the technology in systems. Then we have these integrated cyber physical systems. So these so our project, so actually I told you there are 23 TIHs. So each TIH has different theme. So the TIH of IIT Guwahati has a theme of underwater exploration, technology for underwater exploration. So in as particularly Professor Sahoo has told, so some of you are working on this hydrogen energy also, renewable energy. So we are supporting those projects also. So Professor Sahoo has a project related to this hydrogen storage, and we have given some other problems related to submarine also, and then submarine using this hydrogen fuel, and also similar activities those who are interested to pursue, and which can be applicable this to this underwater area, then we'll be happy to sponsor you also. And for these undergraduate students, so we are giving this internship to the undergraduate students. So 5,000 per month for 10 months we are giving. So those who are interested to work related to this underwater field, then we'll be happy to support you. So we are having a MTech course here in robotics and artificial intelligence. So soon we are going to have a online MTech course on this thing, robotics and artificial intelligence, and also in this AI and ML and e-vehicle. So 3 online open courses will be there. So those who are, you are interested, so you can take up those courses also. And we have several posts actually. So around 148 projects we have floated across our country. So there are 27 startups are running also in our TIH. So this 148 projects, so around 140 JRF are there. So in each project actually one JRF are there. So if some of you are interested, then you can apply for those JRF positions also. And also in the startups, you can work in the startups related to in this field, and you can also incubate. So if you are interested, so you can have incubation here in our TH. So we will help you to incubate, and also we will fund you for your startup. So if you are interested to work in this field, I hope some of you have got some idea, new idea in this field of combustion, which can be a startup also. So you think in that line and then let me know, so that we can fund you in future for your these activities. So I think we have also given some projects to KIT and other places also. So almost all the NITs of Northeast we have covered. So we have given them some or other projects, and also many other NITs we are supporting, and 13 IITs also part of our TIH. So around 200 faculty members are involved in this TIH. So any problem, if you have any problem anywhere, any type of problems you are facing and you want to have a solution, so you can approach either our TIH or other TIH in our country. So they will certainly come forward to help you. So again, let me thank Professor Sahoo and Professor Markus for successfully completing this course, and all these participants also let me congratulate, as you have learned lot of knowledge from this course. I hope you have enjoyed this beautiful campus. So some of you are from this IIT Guwahati itself, and those who are coming from outside IIT Guwahati, I hope you have seen this beautiful campus, and most probably you have enjoyed this 15 days here, and hope you will continue. And for those who are BTech or MTech and want to pursue this PhD, so there are some information also I can give you. So every year for PhD program, so we used to have twice advertise this PhD program. So recently we have completed one advertisement, and this December session we have recruited, we have taken some few students. Similarly in July session also we are going to take students. So there are 25 different schools and departments and centers are there in IIT. So several programs, for example, regular PhD student, part-time PhD student, then this external PhD students. So then if some institute, like for example we have collaboration with BHU, so BHU IIT Guwahati collaboratively they are also floating some PhD topics. Similarly international collaborations are also there with GIFU University, for example mechanical engineering have with GIFU University. So joint PhD programs are also there. So you can, if you want, you can avail those things. So particularly those, if some of your friends are working and they cannot come for doing this coursework, for them also one good thing is there. So there is a course waiver comprehensive exam. So they need not have to come here to do the coursework. They can appear 3 courses, written exam in 3 courses. If they pass, directly they can start their PhD. So these type of facilities are also there, which are not available in other IITs. So you can, I think you can tell these things to your friends or those you know who are interested in doing PhD. So you can also, if you want, you can do some of the online courses. You can start your, those who have not done the PhD, you can start this PhD. And also in PhD we have the facility that you need not have to do all the coursework here. Some of the coursework you can do online coursework also, like from MOOCs or SWAYAM portal. So those things also you can do. And so I hope, so now you know something related to our TIH and this our PhD program, and you will avail all those facilities, and you will take this combustion theory what you have learned and utilize that thing for your betterment in your academic career. So thank you everyone.
So now the last part of this is that we are going to distribute the certificates. I think I request Professor Markus to distribute the certificates to each participants. So while receiving, I think we have plans that we have some photographs, so they can catch a photo and then we can leave. So that is the, so I'll read them one by one. Accordingly, a right position has been created, so they can receive and take a photo. And yeah, please. Yeah. So first is yours, na Mebratu. Okay. So Mebratu. Yeah. You beat them. answer, sir?
Okay. So take this way. Not this way. So.
Chirag.
So congratulations. Welcome.
Pankaj.
Congratulations.
Vikas. Shubham. Anil.
So special person.
Santosh. Kiran.
Thank you.
Amit. Sai Prakash. Sunil. Kavita. Aditya. I think absent. Okay. He is absent. Okay. Thank you, sir.
Thank you.
Thank you, Professor Markus. Now it is my concluding remarks and vote of thanks. So I have thanked Professor Markus, who has come all the way from Germany. So special thanks to them, all the participants who has come all the way and spending 10 days time is a great pleasure for all of us. And most importantly, my special thanks to entire CET team who has worked for this event, starting from initiation of the proposal to materializing, fund arrangement, arranging lectures, streaming, recording, all these things. My special thanks to all the CET team, and we also expect the similar effort in future. So with this, let us conclude, but not the end. Now I invite all of you to join for high tea, which is outside. Okay, so before you disperse, it is requested that one group photo can be taken with all the participants.